This presentation is delivered by the Stanford Center for Professional Development.
Gentlemen, thank you for joining us today. I'm going to turn the discussion over to Professor Shaqfeh, who will get us started with an overview of the energy research that's happening here at Stanford University within the Department of Chemical Engineering, some of the multidisciplinary groups within the School of Engineering, and the interdisciplinary groups within the School of Engineering, School of Earth Sciences, and the like.
Michelle, thank you. Yes, as Michelle said, what I'd like to do is start the discussion by talking about the energy activities on campus, particularly the research activities, and more specifically the spectrum of those activities, which you see up in the upper left-hand corner of this slide. Actually, as given to us by Lynn Orr, the director of GSEP, who's also was making a presentation at the SLAC Science Policy Committee. And what you see there is a spectrum of activities all the way from the fundamental basic science aspects of energy research to the policy, regulation, and law. On the top is are the subheadings for the spectrum, and on the bottom are actually centers associated at Stanford with research activities. The bottom line of this slide is supposed to indicate that we're heavy on the policy and regulation side, and less heavy on the basic science side. And over the last, I would say, 5 to 10 years, that's changing rapidly, where the basic science side, the basic molecular transformations that are associated with energy research are actually growing dramatically at Stanford. And that's part of the reason for this webinar, to actually talk about molecular transformations that are associated with energy and the research that's going on at Stanford. And how that can become available to everybody in the community from an education point of view and outside the community. One of the big aspects of the basic science side is this new SUNCAT, that is Sustainable Energy Through Catalysis Center. It's a center that lives jointly with SLAC and Chemical Engineering, as you see on the logo on the right. And this center is focused on the molecular transformations and basic science part of energy. And this is a very new development, a few years old, but it's already growing, and a lot of the educational activities that are associated with molecular transformations essentially originate in SUNCAT. So the reason that this partnership naturally evolved, that is the SUNCAT Center, which is located at SLAC, and the Chemical Engineering Department, is because more than half of the faculty in chemical engineering are actually engaged in energy research. Every year we have more than half of our undergraduates come to us and say they want to do undergraduate research in energy. And the focus of that research in the Chemical Engineering Department is on molecular transformation. On the right is actually SUNCAT's logo, and not surprisingly, the sun plays a large role in that logo. That's because many, if not all, of renewable energy, alternative energy sources are actually a means of harvesting the sun's energy. And so what you see there is the sun up in the upper left-hand corner, and it's being harvested through a number of efficient and renewable processes. So it's this center and this collaboration that I want to focus on today when I talk about molecular transformations of energy. Also within the chemical engineering faculty, there are many, many other centers, some associated with policy, some associated with the basic science. And chemical engineering, again, plays a leadership role in many, if not all, of those centers, including some of the centers that I'm sure some of you are familiar with who are listening. The people that are associated with these centers include Tom Jaramillo, who's here today, Zhenin Bao, Chetan Khosla, Jens Norskov, Stacy Bent, and a variety of other faculty that we'll touch upon as we go along. Now let's talk a little bit about the role that molecular transformations play in energy research, and why our feeling is that this is really where the technology is going. If there are going to be large breakthroughs in energy research in the future, they're going to be at the molecular level or the nano scale. And I've indicated that in perhaps the simplest situation here on this slide. you can harvest the sun's energy in a variety of ways. The simplest situation is absorption by a band gap material in which you create an electron in a hole. And then an efficient way to keep that energy, if you will, is to produce a fuel with it. These are called solar fuels. And what I'm showing here is the production of hydrogen from the electron that results from the splitting as a result of the sun's rays. And so there are a number of ways to engineer this process. That is the process in the upper right-hand corner. You can either engineer the adsorption. You can engineer the hydrogen evolution catalyst, which ultimately causes the combination of H ions into hydrogen, or you can engineer the oxygen evolution catalyst, which in this particular case is over on the left-hand side. So catalysis, which is the study of lowering energy barriers so such reactions take place, plays a critical role in energy and renewable energy. And the challenge is we need efficient catalysts, stable catalysts, and abundant catalysts, and that usually means catalysts made from earth-abundant elements. And then finally, we need design rules and understanding for those catalysts. And that's, again, design rules at the molecular or nano scale. So, for example, here's some research from Tom Jaramillo's group, who's going to talk a little bit later, about the development of one of these earth-abundant catalysts, that is, in this case, molybdenum sulfide or molybdenite in its natural state in the ground. And the concept here is to engineer activity, that is, activity for the HER, or the hydrogen combination reaction that we showed on the previous slide. What you need to do, it turns out, is to create more edge states. Edge states or feature states in the molybdenum actually are more highly active. And so as you see, there's a variety of textured molybdenum sulfides here that are used for hydrogen catalysts, and those have been engineered by Tom all the way from nanowires to, as you see, fibrous materials. Molybdenum sulfide isn't the most active catalyst for that process. It turns out precious metals are, but precious metals are expensive, and this activity is quite high for a material that's earth abundant. So this is just an example of engineering a molecular transformation that has direct application to energy application. As I said, you could also engineer the adsorption. And so here's an example actually from Stacy Bent's group within chemical engineering, where we're engineering the adsorption of energy by controlling the solar cell. In this particular case, quantum dots. So we're engineering the quantum dot. This is a quantum dot that's created by cadmium sulfide that is distributed in a porous TiO2. And the idea is to layer the cadmium sulfide using the atomic layer deposition process. And if you do that, you control the band gap of the adsorption, and then you control the spectrum of the absorbed light. So you see on the right-hand side different ALD cycles, that is different sizes, if you will, of the quantum dots, have different spectrums of adsorption. And so this is one of the aspects that you can engineer, again, at the molecular level, because you're doing atomic layer deposition to create the solar cell which absorbs the light and creates the ion-electron pair that we talked about in the previous slide. Now, the inverse of electrolysis is a fuel cell. We talked about making solar fuels. A very efficient way of then using those fuels, and one of the examples of those fuels is hydrogen, is through fuel cell operation. And for those of you who don't know, fuel cell essentially is the splitting of a fuel into an ionic species and then harvesting the electrons, and the electrons then produce a current and do work, in this particular case, creating light. So this is a way, an electrochemical way, of using the fuel that you've created from the solar process that I talked about earlier. Again, there's molecular engineering going on because the anode, at the anode you have the splitting reaction of the hydrogen in this particular case, so it can act as a catalyst. You have the electrolyte, which controls the transport of the ions through the cathode side, and then you have a recombination reaction going on at the cathode side to create the waste, in this particular case, the water. So this is a very efficient process that can be engineered molecularly at both the anode, the cathode, and the electrolyte side. Now, modern applications actually would want you to have the production of the solar fuel and the use of that fuel in the same material, the same object. This means that it must operate in the upper left-hand corner in electrolysis mode, meaning you split the water and create the hydrogen, and then on the right-hand side in the fuel cell mode, where you take the H2, which is now the fuel, and return it back to H2O using creating useful work, in this particular case, creating current. It's actually a real challenge to accomplish this, because now the electrolyte, the membrane that sits between the anode and the cathode, actually must be able to operate in both modes, in both electrolysis mode and fuel cell mode. That means it must be able to transport different species in the different modes. And that, again, could be engineered at the molecular level, and it's a soft materials problem. And there's a modified polysulfone, which is down in the lower right-hand corner, a novel polymer membrane design that's being developed at Stanford in order to operate in both modes and have a single device do electrolysis and fuel cells. So again, there's a lot of molecular engineering that goes on in the electrolyte, which in this particular case is a modified polysulfone. So not all inorganic materials are essentially the way to use these solar fuels. One of the fascinating things is to engineer life in order to do these things for you. Again, that's harvesting the sun's energy, but it's usually associated with another fuel, let's say a biomass. You now genetically engineer a bacteria, indicated in red here. The genome is on the left, the enzyme that results from that genome is in the middle, and then the enzymatic pathway is on the right. The idea is to engineer the bacteria so that it produces interesting fuels from the raw materials on the left. Those are called biofuels. So if you're going to understand energy in the modern age, you also better understand something about biology, particularly about bioenergy systems and the genetic engineering of organisms in order to produce interesting and important fuels. So the chemical engineering department is associated with dealing with all of these things, and so if you bring together a set of experts from chemical engineering, they'll be able to tell you about all aspects of this, because our themes within the department are the chemistry of life associated with biology, the chemistry of energy associated with many different elements, and then the chemistry of the environment, primarily associated with sustainability. So what we've done is actually take people, a subset of the experts from chemical engineering together to form this, what we call the MEET program, Molecular Engineering of Energy Technologies, and to make the education available not just to people on Stanford, but to people off campus, including all the aspects of molecular engineering that I talked about in the previous slides. And so that's one of the purposes today, to make you familiarize yourself with the MEET program and what the educational opportunities are with it.
Thanks very much, Eric, for sharing this information with us. I'm going to go ahead and move the conversation over to Professor Tom Jaramillo so he can go ahead and discuss the fuels from sunlight. Tom, thanks.
Great. Thank you very much, Michelle. So what I'll be talking about is making fuels from sunlight. And I'd like to start by asking a question of why would you want to make fuels from sunlight? And maybe we can formulate that question in a slightly different way. We know that solar energy is fantastic. Everyone is a big fan of photovoltaics. It's a great way to get a renewable energy resource to provide electricity for our homes and businesses and potentially even cars and cell phones and things. Wind power is also wonderful. But there are really two big problems, or several big problems actually, in bringing these technologies out to market, especially at a large scale. One of those big problems turns out to be storing that electricity, because we want to use electricity 365 days a year at 24 hours a day. But of course, these resources come and go as they please. So the real question is, how are we going to store that electricity? And there is, in fact, a way to do it already. We can take these renewable technologies and basically feed them into the electricity grid as we know it. And when the sun is shining or the wind is blowing, we can be consuming those renewable electricities. But then whenever the sun goes down or the wind stops blowing, then we have to use fossil fuels, which is where we get 80% of our energy. And by burning things like coal or natural gas, we can provide that electricity in times of need. So one question I'd like for you to think about is what percentage of all the electricity that is moving through the grid, what's the highest percentage that you could be feeding intermittent renewable electricity and still have a stable grid that meets everyone's demand? What do you think it is? Do you think it's 2% of the grid capacity? Do you think it's 30% of the grid capacity? Do you think it's 80% of the grid capacity? Well, the answer is it's 20%. And 20% turns out to be a pretty small number when you think about it. I mean, it's wonderful. If we could have 20% of all our electricity coming from renewables, that would be tremendous. But then 80% is still coming basically from fossil fuels. So we could put a dent into the energy problem, but at the end of the day, we need to find a good way to store renewable electricity. And that's what the context of what I like to share with you is why we'd want to make fuels. Now, there are many different ways that you could potentially be making fuels from sunlight. And in fact, there's many different ways you could be storing electricity. But what I have to show you here on this particular slide is showing you a number of different energy storage modes that we can use already today. We can use pumped hydro, which basically means you use that renewable electricity to pump water up a hill and then let it flow back downhill to get the energy out. There are capacitors, there are batteries. You can use compressed air, where again you use that renewable electricity to compress air and then use that pressure to give you electricity through a turbine on the way back out. But this is on this particular plot where we're showing volumetric energy density in megajoules per liter versus mass energy density in megajoules per kilogram. You can see that compared to these very conventional technologies that we already use today, there is just really nothing that competes with the chemical energy of molecular bonds. We're talking about conventional fuels like diesel, like gasoline, like natural gas, propane, ethanol. You can see that the energy stored in chemical bonds is absolutely magnificent compared to the energy stored in, say, the lithium-ion battery that's in your pocket right now in your cell phone, or in capacitors, or in pumped hydro. So the real question is, well, this slide really shows why we definitely use fossil fuels, because they really are a fantastic form of energy storage. However, the big problems are coming from fossil resources. So the question I'd like to pose to you is, well, is there a way to take advantage of all the wonderfulness that are these chemical fuels, but without the fossil resource? So can we go from, say, fossil fuels instead to solar fuels and produce them using solar energy instead? So let's think of a way that we might do that. So here's a typical way an engineer would think about the problem. You basically draw a black box, and you say, I'm going to feed something in and get something out of it. So what might we feed in? Imagine feeding in water, feeding in carbon dioxide. These are obviously extremely abundant molecules. Everybody, all of us, we're all breathing these molecules right now. And imagine shining some sunlight onto that black box. And when you shine that sunlight, you provide some energy, which is going to allow for some chemical transformations. We can start moving and rearranging some of these atoms around. So what are our output streams? We can have oxygen as one of our output streams, which is a useful molecule, of course. But take a look at all the different things that we could possibly make when you feed it into this black box. We could be feeding in things or getting an output of, say, alcohols, which could be certainly used as fuels. We could get some gaseous hydrocarbons, as you see here, with methane and ethylene. We could be making liquid hydrocarbons, which are the conventional fuels that we put inside our cars and trucks. And no matter how you rearrange the bonds, anything that you'd be making here could actually be used directly as a fuel. I'd like to point out that all of these molecules that you see here have mass energy densities that are within a factor of 4 of that of gasoline. So they could be actually used in a standard internal combustion engine to get the energy back out. A second option is to actually use these molecules as chemical precursors to then make whatever it is that you're after. So, for instance, if you made carbon monoxide and hydrogen, you could feed those into a Fischer-Tropsch plant and make diesel and gasoline. This is here-today technology that is already operating at scale around the globe. So the point is, what we've done with this is we've come up with a process where you can shine light and have a feed of just water and carbon dioxide and make pretty much any molecule that you'd want to use as a fuel, or molecules that you'd want to use to feed into the chemical industry to make the things that we use every day, like the high-density polyethylene that goes into making milk jugs. So the question is, what is inside that black box? There's many different possibilities, and what we're working on in my laboratory is we're trying to figure out electrochemical ways of doing these chemical transformations. And we're interested in electrochemical technologies because we know that, say, wind and solar technology are very good at producing these renewable electrons. This is a way that we can just feed these electrons into such a process where you can, again, grab that carbon dioxide and use the energy here, the uphill energy that we need, so that we can start converting it back into a fuel, which you can then burn in your car. The CO2 goes back into the atmosphere, but then you just recapture it and then recycle it through renewable energy to complete this cycle, which is a net zero emission of CO2. So in this particular case, we've got two separate devices that do the process, or you can imagine more advanced modes where you have an all-in-one device, where a device like this is basically, it looks like a photovoltaic that's immersed underwater, and when you shine light onto the semiconductor, you excite electrons in holes just like you would in a photovoltaic, but then you can actually do the chemical transformations with water or CO2 to make the different products that we've already talked about. So let's talk about how we start attacking this problem. Either way you go with either of these options I showed you on the previous slide, it's really all about moving atoms around, moving molecules around, rearranging bonds. And so these are the three reactions that we're really focusing on quite a bit in our laboratory. You take protons and electrons, you make hydrogen, or you can stick protons and electrons on a carbon dioxide to make fuels and chemicals. And of course, both of these reactions need protons and electrons. Where are you going to get them from? You can get them from a nice, inexpensive, abundant resource being water. So if you oxidize water to O2, you release the protons and electrons that you can use for this process here. If you read all these reactions left to right, that would be the fuel production reaction. That requires energy input. But of course, once you've made these molecules, you want to get the most energy back out of them. And so we're going to try to drive these reactions right to left. So we need to develop catalysts there as well. And that would be the fuel consumption mode. And the way I want you to look at these reactions is that the fuel production mode is energy in. The fuel consumption mode is energy out. And so that if we want to use chemicals as a means of storing renewable electricity, whether it comes from wind or solar, we basically want to get as much out as we can and put as little in as we can. And if you divide those two numbers, that gives you a sense of the round-trip efficiency of storing storing intermittent renewable energy in the form of chemical bonds. So as I've already mentioned, it's really all about catalysis here. A necessary but insufficient condition for something like this to work on a large scale is you need good catalysts that are able to rearrange these bonds as we would like. And so this is the research approach and methodology that we take within our group. To do that, we basically design materials. We hypothesize what are interesting materials to drive these reactions, what would be good surface structures, what would be good stoichiometries. And we get this inspiration from a lot of places. We do some of our own theory to help guide us. We also collaborate with people like Jens Norsko, who's a dedicated theoretician, to really guide experimentalists in terms of materials design. And then we do a lot of synthesis in our laboratory, really focusing on nanomaterials, because when you make things like nanoparticles or nanowires or nanoporous materials, these types of materials will exhibit properties both at the surface and at the bulk that are different from what they would conventionally be as a large particle. And then once we make these types of materials, we do a lot of microscopy and spectroscopy, because at the end of the day, what drives these chemical transformations these are all atomic scale events, molecular scale events. So we need to have atomically resolved images like this one. These are atoms that you're looking at of a gold nanoparticle catalyst. We need to see how those things are arranged at the surface. And we also need to do spectroscopy, where we measure the electronic band structure. We literally look and see what are the energies of the electrons in this material, because it's the electrons that are really participating in the reaction, whether you're going backwards or forwards. And so once we've synthesized and understood our material through and through, we can do our catalyst evaluation, which tells us what works in terms of activity, selectivity, and stability. We can take that information and feed it right back into materials design to develop the next generation system. So at this stage, with the last couple of minutes, I'd just like to show you a couple of examples on some of how we adopt this methodology in developing catalysts for hydrogen and for oxygen reduction, as well as for CO2 reduction. And there's not enough time to go through all the details. If you're interested in the details, I would certainly encourage you to look at some of the references that we've published recently in this area. But here's one case of looking at some core shell molyoxide, molysulfide nanowires that we've developed for hydrogen evolution catalysis. And the point I'd like to make here, as Eric alluded to earlier, if you look at this plot, basically this is ranking a whole bunch of different catalysts. And where you really want to be on this plot is down in this corner, where, not surprisingly, the precious metals are the best. But there are big questions as to whether precious metals could ever scale in terms of energy, because we demand so much energy on this planet. It's 17 terawatts and climbing. It's not clear that precious metals could even satisfy all our needs by mining them at the rates that we would require, which of course would hike up the price to a point where it's probably not going to be cost competitive versus fossil fuels. So in this case, we're trying to develop non-precious metal catalysts that are scalable. And here's the moly sulfide, which is not quite as good, but it is certainly better than a lot of the other non-precious metals out there. And in this particular design, we grew these nanowires where we grew these nanowires with a core shell structure to decouple two different important processes. To do electrochemistry and electrocatalysis, you need to be able to move electrons up and down these wires, but you also need a good catalyst surface. And so it turns out that by making a core that consisted of moly trioxide, which is very good at conducting electrons, and then put a shell of just a couple of nanometers of MOS2, which is a good catalyst, we were able to get extremely active and stable hydrogen evolution catalysis that could actually operate in sulfuric acid for years and years based on our accelerated durability testing. Now, the one thing with this moly sulfide is that all the action turns out to be happening at these edge sites, and if you take a look, there's really not a lot of edge sites around for these core shell nanowires the way the moly sulfide grows. So another project that we've been working on is how do you expose more edge sites on the moly sulfide? So we've come up with these nanoporous structures, and as you can see, by basically having a really tight radius of curvature, the moly sulfide has no choice but to basically expose more of these edge sites. You can see the TEM images here where we have porosity on the order of about 4 nanometers diameter. And at the end of the day, when we take a look at the data, we're comparing this data is with this nanoporous material versus this data for the core shell nanowires I showed you on the previous slide. Basically, any way you cut it, at any potential that you might operate, you're going to get 1 order of magnitude, 10 times as much current density out. So these catalysts are 10 times as good because we were able to expose more of these edge sites. We've also adopted some of these approaches in making fuel cell catalysts. So the conventional fuel cell catalyst consists of platinum nanoparticles. And so by making nanoporous designs of platinum, although they don't have quite as much surface area as the nanoparticles, they turn out to be more active per site than the nanoparticles. And so if you look at this bar graph where we do repeated durability testing, 10,000 cyclic voltammograms, which simulates 2 to 3 years of fuel cell operation, you'll see that in red, this nanoporous material is not only better than the conventional nanoparticles used, but it's also much more stable after this accelerated durability testing, whereas you can see the nanoparticles basically lose activity over time because these nanoparticles are not very stable. They will sinter together, they'll clump up, or they'll detach from a surface, never to be seen or heard from again, whereas the contiguous thin film of a nanoporous material is much more inherently stable. And then finally, I'd like to just point out some of the work that we've been doing in terms of carbon dioxide conversion to fuels and chemicals, which really started with electrochemical engineering of a reactor where we could do this chemistry and measure products simultaneously, both gaseous and liquid products of reaction. And to make a long story short, on a copper surface, if you had looked back in literature for the past 40 years of research in this area on copper, if you looked at every product ever produced by any laboratory anywhere around the Earth, there would have been a grand total of 10 different products observed. In our electrochemical reactor, based on our new methods that we've adopted, in one set of experiments, we saw all 10 of those that everyone had ever seen in the history of this field, plus 6 more that no one had ever reported on. And so not only did we see them, we were able to quantify, and you can see all the products being made here. These are really wonderful products. We have carbon C1 products, C2 products, C3 products. We've got hydrocarbons, we've got alcohols, we've got carboxylic acids, ketones, aldehydes. Some of these, by the way, are in the global top 50 of chemicals produced, like ethylene glycol, for instance. When you're in the global top 50, that means you're making billions. We already, currently today, are making billions of kilograms per year of these products. And if you do the math, with 7 billion people on the face of the Earth, that means that every man, woman, and child on the face of the globe is responsible for 1 kilogram per year of some of these molecules being produced. So the question is, can we produce those molecules instead of from a fossil resource? Can we make them from a renewable resource? This reactor, something like this coupled to renewable energy, could in fact do that. But where we're at scientifically today, we're not ready, I think, to commercialize this type of process. What we need to do is understand what makes these catalysts work, and why does copper make all these broad ranges of different types of products. So we've quantified where in the potential scale they do it, how much current do we get, and that allows us to actually construct reaction networks and do some mechanistic analysis. And this is basically providing the insight that we need to develop better catalysts in this field. So with that, I'll just conclude by saying thank you to my team for doing all the work that I just presented to you today, and thanks also to the U.S. Department of Energy and the National Science Foundation and the Global Climate Energy Project for sponsoring this research. I'll turn it back to you, Michelle. Thank you.
Thanks very much, Tom. I appreciate you sharing this research with us. And now I'd like to turn it over to Ricardo Levy, who is going to talk about some of the entrepreneurial challenges around these energy industries and the science-based industries. Ricardo.
Thank you, Michelle. First, I'd like to thank Tom and Eric. I think that was fascinating, and it's been a long time since I was a student. I'd love to become a student again. But more to the point, I've spent 3 decades building businesses in technology areas, many in the energy area, and there's a lot of stuff here that can be developed further. We're going to switch gears now somewhat from the previous conversation, and we're going to move into the subject of teams, especially in our deep energy-related topics, which take longer term to develop and definitely are multidisciplinary. The issue of teams becomes essential. So what I'm going to talk a little bit is about teams, team leadership, which here at Stanford we feel is maybe not as important as the innovation and the invention, but at the end of the day, if we want to take these commercial, the teams have to be effective. So I'm going to be talking about 2 topics related to team leadership. So I'm going to talk about a couple of roles of the intra-entrepreneur, key roles of the intra-entrepreneurial leader. And the first one I'm going to talk about is maybe a little unusual, and I see the leader as being a risk adjuster. So obviously, as many in our audience who are deeply involved in commercial enterprises know, teams are really at the heart of the innovative effort. And as we know, the best teams have a spectrum of skills and expertise. And every team leader knows that there is going to be a variety of capabilities in a team which kind of make up for the richness of the team and the effectiveness. The one thing most of us don't pay that much attention to is that a team will have a spectrum also of risk attitudes and risk aptitudes. Different members of our team have, if you will, different risk appetites. For example, and this goes back to my own experience, a scientist will be very, very comfortable with pushing the boundaries of technical know-how. So the comfort zone of the scientist is in the technical uncertainty. But you bring the scientist into an environment where there could be major financial uncertainty, which is the case when you're an entrepreneur and you start a company, and their comfort zone is very different. I have many cases in my experience and in my business life where I know specific individuals who were fearless as they entered the unknown and pushed the limits on the technology side. But when we turned the discussion on what's the runway of the company and how much cash we have left, there was an enormous degree of, if you will, fear. But the fact is that you need to handle both in order to be successful, both the technology uncertainty and the financial uncertainty. So the key role then of the leader, in my way of looking at it, is to absorb uncertainty, to absorb that difficulty that our team members may have in coping with some of the issues that may be outside of their particular domain or even experience level. And we do that in order to release the team members to do what they are best designed to do. And at the end of the day, it all comes down to trust. And in fact, I have a very simple-minded way of looking at it. Now, it's simple-minded, but it served me well over the years, both as a leader of a company, but also now lately as a board member to understand the burden that CEOs carry. And the way I envision it is every time you attract somebody to your team to become part of your journey, you are really entering a relationship. And I envision it as you receive a trust packet. And it is a real eye-to-eye contact. It's a deep contact. And the result is that you create a covenant between the two of you as the leader puts the trust packet in his backpack. Now, this may sound funny as a symbolism, but I tell you, so often as I am in meetings and I watch leaders of young new companies handle some of the issues, I can personally feel how their backpack is getting filled with all the issues they have to go to. Now, the challenge, of course, is that the backpack gets heavy as more and more responsibility is taken upon oneself, and it is a very lonely journey for the leader, which really raises this whole range of interesting questions of how does a leader cope with the increasing responsibility and the loneliness that comes with, in effect, being at the top, in particular when you're dealing with a new venture, either within a large organization or in a private company. And it's a complex subject, a very rich subject that we do cover in some of our work that we do at Stanford, and I may allude to it at the end. But I want to now switch gears to a second topic that has to do with the role of the entrepreneur and the entrepreneur to know how to lead, to know when to lead and when to manage. So as we know, in small companies, in particular when we are resource constrained, we wear many hats. And the leader is very often asked to also be a manager. And long-term projects, as many of you who are listening to this know, we have to do many things, and some of them require leadership, some require management. And to be effective, we have to understand the difference between managing and leading. And this is a topic that I knew subconsciously over the decades, but I really never started looking at it more specifically, and yet it's a very simple concept, but when you look at it more specifically, I think you understand some of the dynamics. And I'm going to quickly go through some of the different aspects of leadership versus management, and I realize we are running short of time, so let me go rather quickly through this. I'm going to just touch on some of the key elements that differentiate leadership and management. A leader points, a manager plans. A leader aligns, a manager organizes. A leader inspires, a manager problem solves. A leader produces change, a manager produces predictability. These are very different strengths and very different inclinations. So let's just look at this briefly. A leader points. Basically, as we know, the leader is chartered with defining a vision and direction. A manager plans, establishes tasks, budgets, programs. A leader aligns. We know that a leader has to be a good articulator that engages the team in the direction they want to go, whereas a manager is chartered with identifying skills in staff. A leader inspires, motivates, creates the culture. A manager problem solves, foresees, and addresses hurdles. And finally, a leader produces change, expands our horizons of the possible, and the manager assures that we can reach them. It's a very rich topic, and I highly recommend that you go to this particular Harvard Business Review report. Please jot it down. It's called What Leaders Really Do, and it captures the elements of this particular important subject. So let's touch briefly now on some of the things that we can do to both be able to do the leadership and the management task, and at the same time not lose sight of our responsibility to absorb uncertainty. If I can have the next slide, please. It comes back to the ability to understand yourself as a leader, both in terms of your inner characteristics, your outer characteristics, and your core characteristics. And there is a lot of richness inside these topics. They define the various stages, in effect, as you engage a team to create a new venture or a new business. The inner characteristics are key in the risk capacity, the outer characteristics in the persuasion capacity, and the core characteristics in the execution capacity. The things to keep in mind as we go into this topic is it's very important to know your own propensity. In addition, it's important to sense when it's time to lead and when it's time to manage, and to act on both of them in a consistent way that is genuine and with integrity. Some obvious things: if you need management bolstering, you can get good training, and even after 30 years of having been a leader and a CEO, I still find that I can learn more and how to become a better manager. If you need leadership sharpening, something that has been extremely effective in my life, and I highly recommend it, and many have this experience, is to get a good executive coach or mentor, which creates a good secondary and clear vantage point. And finally, and perhaps most difficult, when building a team and when hiring, we need to appreciate good managers, but we need to make sure we don't confuse good management with good leadership. And I won't bore you with the details, but I have many situations, failures, where in fact I have missed this, and I've not been very happy with the consequences. So the bottom line is that we need to be very thoughtful about this. And I want to close with a leadership alert, which is in particular important for the entrepreneurial leader, and that is to be careful with the syndrome that I can do it faster and quicker myself. And on that note, I turn it over to Michelle.
Thank you very much, Ricardo. I appreciate you sharing that insight with us. And now I'd like to very quickly share some information about the host of this webinar session, the Molecular Engineering of Energy Technologies, or as you've heard us affectionately refer to it as the MEET certificate program. They have hosted this session, and I'd like to bring Professor Shaqfeh back into the discussion and just ask a couple of questions to learn a little bit more about this. Eric, if you can help us understand, what was the inspiration for creating this new certificate program within the Chemical Engineering Department?
So I touched upon it a little bit before. We have, more than half of our undergraduates and a large fraction of our graduate students who want to be educated in energy research, modern energy research. From our point of view, the critical transformations that are going on in developing new energy technologies are all molecular and nanoscale technologies. And then we realized that education was very, very valuable for other people that are already in the field. So we decided to bring together a subset of us who were particularly interested in energy education, broadly speaking, to talk about molecular transformations and to approach the problem from all different facets, from the bio facet, from the catalytic facet, from the energy absorption facet, from all different molecular facets. And we put together a number of what I think are great and mostly brand new courses, just out of the enthusiasm of our faculty to spread the word in some sense.
And why is this topic so important right now and so relevant to industry?
Right. Well, all relevant alternative energy technologies, essentially to fill the energy demand. I noticed the first question today, and we're going to get to that, is what is going to keep the focus on alternative energy. Part of the thing that's going to keep the focus on alternative energy is just simply demand. Even if we get all the unconventional oil out of the ground, our demand is going to outstrip our fossil fuels. So there's going to be a focus on energy for the foreseeable future, and there is a real feeling now that there's an understanding of the environmental concerns. And so we feel like all technological achievements in this area, breakthroughs, if you will, are going to be at the molecular level going forward. So that's why it's very important right now.
Excellent. Well, thank you very much, gentlemen, for participating in the presentation today and sharing your research with our audience. Okay, so The first question that we received today is, with the windfall opportunities right now in the U.S. and the production of unconventional oil and gas, how will the U.S. maintain focus on the basic research in renewable energy sources? And I'm going to go ahead and turn it over to any of our speakers that would care to answer this question.
Oh, thank you, Michelle. So that's a really good question, and especially with shale gas, which is a very hot topic right now. So it's an interesting history, with modern history, I'll call it, of this unconventional shale gas. If you had asked somebody 5 years ago, then the fossil resources were looking pretty bleak. If you asked somebody 2 years ago, it would have seemed that there's so much natural gas that we're good for the next 200 years. And but now the temperament has changed once again, and so it's not so clear anymore that we're going to have hundreds of years worth of natural gas. But we will probably have on the order of a couple of decades worth of natural gas, which I think is good news for all of us. I consider it to be a stopgap solution. It is something that it's a technology we already have at scale, and therefore we can use natural gas. What it's going to do is buy us some time to allow renewables to get to where they need to be to ultimately be the long-term solution. So from everybody that I've talked to at the U.S. Department of Energy, and this includes Secretary Stephen Chu, who I met personally a few months ago, and asked him this very question, it's not clear that the natural gas is going to continue long enough for us to be able to rely on that. We need to get renewables onto the market, and that is going to take a while. It will take decades. Even if we had viable solutions here today, it would take decades to roll these technologies out at the terawatt level, which is where they need to be to ultimately replace fossil fuels. So this unconventional oil and gas, again, is pretty much buying us time is the bottom line.
Thanks, Tom. Let me add one more thing to that. The shale oil, there are lots of technological challenges with getting shale oil as well. So in the chemical engineering department, there's a whole separate research climate and research experience with shale oil, and there's a lot of money coming in to the chemical engineering department to do shale oil research. So there are real technological challenges there to get, quote unquote, all of that oil out of the ground. So I think that will, if you will, compete in the short term with the technological challenges for renewable energy sources as well.
Just a final thing here. I think the key issue, and I've been in the biomass to electricity business for a number of years, the key issue is really the cost. And I think that goes right back to the technology. And I think what we need to do as scientists and technologists is to find those breakthroughs that take us 1 or 2 orders of magnitude past the point where we are now. Because if that happens, we start moving away from needing government subsidy, and we start being competitive. And I think if we do that, then there are a lot of opportunities for new businesses.
Thanks very much. The next question that we have is the 20% renewable a max that the current grid can handle, and what is the reason for the 20% requirement for many states?
Great, I'd be happy to address that too. So about the 20% requirement for many states, that's definitely a policy question, and actually I don't know what fed into the policymakers deciding on the 20%. They could have actually been talking with technical folks, I would hope, and realize that the max is 20%. At least with the current grid, but the 20% is not for all grids. It's actually for a very smartly designed grid, and so actually a lot of grids in the United States, we have an aging electricity grid, can't even support the 20% that's stated. So the reason for that is again, if you're going to be incorporating these renewables with intermittent resources, you need to be shuffling energy around all over the place at a moment's notice if the wind starts dying down or if a cloud passes overhead and starts blocking the sun. And so this is what's giving the technological reason for the 20%. It could potentially be pushed higher, but there's going to be a fundamental limit, because if it were 100%, at the limit of 100% coming from intermittent renewables, you can imagine once the sun goes down, you're not going to get any power out of that. So 20%, it's still a ballpark number. It could be pushed a little bit higher up depending on how smart you're willing to engineer a brand spanking new grid, if you're going to design a brand new city with a brand new grid. But that 20% number is pretty much a maximum. So we need good forms of energy storage, however that might be.
Thank you. The next question is, the sunstorms affect the magnetic field of the Earth continuously. Is there a way to harness this? I don't know if there's...
I'll go ahead and answer this. I would say that there are many, many, many ways to harness energy, and I am sure that there is a way to harness it. I am also sure that right now there would not be a cost-effective way to do it. And that's really the question, could there ever be a cost-effective way to do it? And so I'd like to say that in chemical engineering, that's one of the advantages of coming from this field. You know, one thing that we do really well and we teach all the time is scalability and how to scale up processes to really large scales. And so, you know, the way I would look at a question like this is I would say, well, let's do a techno-economic design of basically, let's look at a technology, let's pretend that that technology actually works in terms of harnessing this energy source, and then let's build a plant around it that would actually provide electricity continuously based on that phenomenon. And so you can do all the costing, you can do a lot of the costing without having the technology in hand yet. And I think that's a really nice way to steer us into what are the most viable options, because we can at least get a baseline price of what it might look like if one were able to develop the technology to be as efficient as one would hope it to be.
Thanks for taking that one, Tom. Another question, can salt or sodium be used to store the energy?
Absolutely. But of course, but you're still talking about chemical conversion, so this is kind of a unidirectional conversion where if you had a sodium metal, for instance, and, you know, just to make things really simple, you throw it in water, it oxidizes like crazy and releases tons of energy, but then you've done it one shot, you've got to get it back into a metallic sodium state. So how are you going to do that? You're going to need energy somehow. And so it's a different way of looking at the problem. Can it be done technologically? Absolutely. But it's probably not going to be as reversible because really, again, you can think of it as an energy in and energy out. How effective are you at putting as little energy in as possible to reduce it? And any scheme that I have seen to date that uses this type of concept basically requires too much of an energy penalty, so it doesn't look like a cost-effective solution. I've yet to see a cost-effective solution come out there, but I don't want to discourage anyone from thinking about it because there could very well be some way of taking advantage of that type of conversion. Excellent.
And another question is, does spectroscopy play a role here?
I'll answer it because I teach the class. So Chemi 345 is spectroscopy, molecular spectroscopy, and it absolutely provides a major role because spectroscopy is our eyes and ears when it comes to molecules. We cannot see atoms, we cannot see the molecules, but we can shine light on the molecules. We can throw electrons at the molecules, and we can see how they respond. So it's basically our molecular eyes and ears. So if you ever want to be effective at developing a technology that can do conversions between molecules, you need to see how they're behaving. Spectroscopy is how we see how they behave, not to mention the materials themselves and how they interact with those molecules. So spectroscopy is a fundamental basic science that is a part of any energy technology that ever gets rolled out.
Yeah, let me follow up a little bit on that. More than a decade ago, the chemical engineering department decided to have spectroscopy as essentially a key feature in our curriculum because we realized that most of the engineering in the next few decades and going forward was going to be molecular, and that it was going to be critical for students to understand molecular probes, including spectroscopy. So we now have Tom's course as a staple of our curriculum and have for more than a decade.
Excellent. And we do have one additional question. What is the dollar cost and energy cost of manufacturing the Nano Porous catalyst?
So the answer to that question is it's expensive right now, and that's because we're developing these materials in our laboratory, and so since this is a research grade activity, you know, right now we're not thinking about minimizing the cost at this point. We're trying to make the best material that we can, and then once we make it, as long as we know that it comes from earth abundant materials, then we can envision a pathway to making a scalable route to that type of a material. So the answer is times T equals 0 as in right now. It's not a cheap way to do it, but it can absolutely be made inexpensively. There is no doubt about that because molybdenum and sulfur are two of the cheapest, most abundant elements on the face of the earth, and it can scale to the terawatt level no problem.
Excellent. Thank you very much. And so with that, I'm going to thank you for joining us today for our presentation.